This is the introductory video for the Physics 1101-1120 Ideal Spring Experiment. In part A of the Ideal Spring Experiment, we're going to be testing Hooke's Law. The way in which we do that is we'll put some masses on our spring, which is here by the way, and we'll see how far down that extends the spring. We're going to do that for a variety of masses, and then we're going to make a graph of the force that we applied to our spring versus the extension, that is how far down it stretched. And Hooke's Law predicts that we should get a linear graph and that we'll be able to find our spring constant k from the slope of the graph. The units on the spring constant, by the way, are just newtons per meter. So a spring constant is just a measure of how far that spring stretches per unit of mass. So that's something that's set by the manufacturer, and it's a constant for any given spring. Now before we start, we first want to zero our apparatus. So we take all the masses off. And right here we've got a numbered scale. It's a centimeter scale. And we want to adjust this up and down so that the 0 mark on the scale is lined up with the bottom of our mass hanger here. So to move this up and down, you pinch these two things and then you can slide your scale up and down. And you want to line up the 0 with the bottom of your scale. However, we want to do this fairly accurately, and there's no good way to do that when the mass hanger is over here and the scale is over here. So if you take this guy off and have a look at the bottom of it, there is a little pointer that you can rotate out. So just a little arrow. And you want to arrange for that to very lightly touch your scale. So you have it just barely touching the scale, and then you can very accurately move the scale so that the pointer is lined up with 0. Now the extension of the spring is always defined as being the final position minus the initial position. So by making our initial position 0, we're just making the math easy for ourselves. Our final position will always be equal to the total extension if the initial position is always 0. So zero your scale carefully, and then you're ready to begin. The maximum amount of mass that you should put on the spring is only going to be 300 grams. So that's the absolute maximum that you should use. And you don't want to go over that because you might damage the spring itself. You could actually stretch it out permanently. So 300 is our maximum. And to get a good graph, generally speaking, you want to span the entire range of data that you can. So that would normally mean that you'd want to go from 300 right back to 0. However, I actually recommend that you do not use 0 as a data point. In other words, don't make this your first data point. I recommend that your first data point be no less than 40 grams. And the reason why is just that you do get points on your graph that would be nonlinear when the masses are very, very light. So make 40 or even 50 your minimum and go right up to 300 grams. So you span the entire range of data that is possible, and that'll give you the most accurate graph. So the data that you're going to record is going to be the total mass that you dangled off of the spring. I'll tell you more about that in a moment. And also the extension of the spring. So again, double check that the pointer is lightly touching the scale, and remember, impatience is not a valid source of uncertainty, so if this is bouncing around a little bit, either steady it or wait for it to settle down. So you would add your masses, record the extension, and then you could move on to your next set of masses and see how far down that extends the spring. And as I said, you want to span the entire range of data that is possible, and you get to choose what mass increments you want to use. You need 6 to 8 data points for your graph, so you can figure out what sort of intervals to choose in order to span your entire range. Now the quantity that we're going to be graphing is going to be force, which is mg, where m is the total mass hanging off of this spring. However, that's the total mass, not just the masses that we added, but also the mass of the mass hanger itself. So you can take this off of the spring and then go and weigh it. Now different lab instructors have different policies about how they want you to handle the uncertainty of the total mass, so you should clarify with your lab instructor what they want. The most common thing is that they would tell you to use the instrument uncertainty of the scale for the mass of this, and to assume that the masses of these guys are exact. That is, that the manufacturer did such a good job that the instrument uncertainty on these masses is negligible compared to the instrument uncertainty of our scale when we weighed the mass hanger. However, while that's the most common thing that lab instructors ask you to do, it's not the only way that they might suggest you handle it. So other lab instructors might, for example, tell you to add the masses and go and weigh it as one big blob, and then just have one uncertainty for everything. But that would mean that you'd have to weigh every single increment of mass that you used individually. Another way to handle it would be to weigh this guy, have an instrument uncertainty due to it, and also assume that all of these have individual uncertainties. So as I said, there's a variety of ways your lab instructor might ask you to handle the uncertainty for the mass. Clarify it with them. So you would graph your data. You would get k, your spring constant, from your slope. There is no known value of k that you're given, so you don't need to compare it to anything, but you should check whether your y-intercept agrees with 0 with an uncertainty. In part B, we're going to use simple harmonic motion to determine the spring constant k of a small spring. Now on the apparatus there is this centimeter scale which you won't need for this part of the experiment, so you can pinch these two clamps and move it out of your way. What we're going to be doing is we're going to add masses to this mass hanger, which stretches out the spring, and then we'll lift very slightly to start this thing bouncing. And you'll notice that it bounces up and down in a very regular way. So this is simple harmonic motion. We're going to time the period of oscillation, so that's one complete up and down motion. And we're going to make a graph of that period squared versus the total mass that is hanging on the end of the spring, including the mass hanger itself. According to the theory, that should give us a linear graph, and then from the slope of that graph, we'll be able to solve for our spring constant k. Now in this part of the experiment, the slope is not equal to k. We do have to solve for k, using the value of the slope that we get. So to time the 10 oscillations, you would simply wait until it's at the bottom of its bounce, and then start timing, and then count off 10 of these. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And then this value divided by 10 gives us the period of oscillation. So you need the period, you also need the total mass that is hanging on the spring, so that's not just the added masses, but also the mass of the hanger itself. So if you haven't already done so, you take this off and you weigh it. Now you need a graph of all of this data, and you want 6 to 8 data points, and the range of masses that you use should be from 150 grams up to 300 grams. So it's a smaller range of masses than what you used in Part A. So you'll probably want to rethink the mass increments that you're using in order to get 6 to 8 data points between 150 grams and 300 grams. So do use your smaller masses for this. So for each of your mass increments, you time the period of oscillation, and you also record the total mass that is hanging on the spring. And then, if you look in your lab manual, equation 4 is the theory that governs this part of the experiment. And if you compare that expression to y equals mx plus b, you see that the theory predicts that if we plot the period squared on the y-axis and the total mass on the x-axis, then our slope should be equal to 4 pi squared over k, and our y-intercept should theoretically be equal to 0 with an uncertainty. So you would graph all your data, find the slope, set it equal to 4 pi squared over k, and then solve for your k value. You should also check that your y-intercept does equal 0 with an uncertainty. Now there's no known k value that is supplied to you, but if you did Part A of this experiment, you should compare the k value you got in Part A to the one you got now for Part B, and see whether they agree with each other with an uncertainty. And one last thing that I'll mention is that 300 grams is the maximum amount of weight that we want to put on this spring. So in order to protect the spring, don't pull down on it, push up to start it bouncing. You also want a fairly small oscillation, so only a few centimeters in total.